the two group, and then our classification results, and I'll talk about some applications in future directions. And this is joint work with Dan Berwick-Evans, Laura Murray, Apurva Nakade, and Emma Phillips. So first, before we get to any smoothness, what is a two group? So it's a categorical notion of a group. So instead of having a set with multiplication, we have a category with multiplication, but the axioms should only hold up to isomorphism. So the data of a group normally is an identity element, a multiplication operator, and something that takes inverses. And here, this is going to be an object of the group, and M and I are going to be functors. So I've written what they do on objects, but they should do something on morphisms too in a compatible way. And then rather than having a list of axioms, we have a list of isomorphisms, which is further data that we want to keep track of. So for example, multiplying 1 and G should just give me G. It should be isomorphic to G on both sides. If I multiply G and H and then K, it should be the same as multiplying G with the product of H and K. And thing about inverses. So these are all going to be natural transformations, and that if I had morphisms between the objects G and H and K, I would get a bunch of commutative diagrams, and they should be compatible with each other, satisfying some compatibility conditions, some of which I'll explain later. And so again, all of this is data that is part of the group. So if we keep this the same, but we change this, it's a different two group. And in particular, we're interested in the associator, this guy here, which we call alpha. Well, that's the only one I've given a name for this talk, because that's the one that we'll talk about.
So is there an explanation why they're called two groups?
Sort of in the categorical sense that you start with sets are 0 categories, and then categories are 1 categories, and then 2 categories. So if groups are just the ordinary thing, then when we go up the category level, we just increase.
It's not to annoy finite group theorists.
Yeah, that's true. Yeah.
Two groups. So two groups.
My colleague did have someone leave in the middle of the talk, or quite early in the talk, because they wanted to hear about Silov theorems or something. I don't know. Yeah. I think this is pretty standard notation now. But earlier you might have seen some people called them GER categories. It's like a group category. Or categorical groups. So here are two equivalent formulations that maybe motivate some of that. So G is a monoidal category. All this structure here with the associator is saying that it's a monoidal category. We can have tensor products. We have the additional condition that all objects have tensor inverses. So this would be like a category of line bundles as compared to vector bundles. And then another way to think about it is that it's a group object in the 2 category of categories. And there's various flavors. So some people, maybe you don't require that you have a specific choice of inverses. You just require that inverses exist. And so you have different adjectives for your 2 groups, but it's not too important.
Emily, in a 2 group, could you have more morphisms than just? There's no requirement that these are like
Yeah, for sure.
like tons of morphisms, other morphisms around.
Right. Like so the category of line bundles is a 2 group. It's a special example because it's abelian. And so line bundles have automorphisms, but we pick out special ones that give them. Okay. So let me say a little bit about one of the conditions that alpha satisfies. So it satisfies something called the pentagon axiom, which if you've read about monoidal categories before. And so it's called the pentagon axiom because we start with 4 group elements instead of 3, and we put the brackets in different ways and we move them around, and what we get is a cube. That's why we call it the pentagon axiom. So over here we have our 4 group elements. And then maybe I multiply the first 2. So I multiply G and H, and then I multiply that with K, and then I multiply everything with L. And so that's this path here. Or if I want to start multiplying on the right, then I multiply the last two, and then again the last one and the last one. So that's be this operation over here. And if you look at, oh, I have to keep going. Most of the faces here, like the front face of this cube says is the associator. It says that if I first multiply the things on the left and then multiply again, or multiply the things on the right and multiply again, commute. So we have 5 faces that are given by associators, and the top face is a stupid face.
So it's a little bit like an A3 category, would you say? No?
I'm not completely familiar with that term.
Well, there is this, two categories, category where you three categories where the multiplication of morphisms has an operation mu3, which is like an associator. And then
How is that different from a monoidal category?
well, I think it's different because in the monoidal category, right? So, if in the monoidal category, you can also multiply objects. So,
So I think this is more like a monoidal category.
There, the non-associativity is in the composition of morphisms. It's here the associativity is important on the.
so the
Right. So if I look at,
You have to like,
so G would
look at
be
point
the
mod
morphisms
G.
in that case.
yeah,
In the sense that here you act on the group, there you act on morphism only. But you have a category, A3 category with one element,
Mhm.
then it was.
And it's all morphisms are inverted.
Yeah.
Okay, so that's what an abstract two group is, but now we want to add some geometry. And so if we were totally going by analogy, we would say Lie two group, but that word's already taken. So we say smooth two group. So we kind of have this table where we can generalize in different directions. If we start with a discrete or an abstract group, which we just, we all know, it's a group object in the category of sets. And then we've just seen that we can change our set to be a category. And so we get a two group, which is a group object in the two category of categories. But we can also go this way, where instead we change our set to be a manifold. And so we get a group object in the category of manifolds. And now we want to do both at once. So, I mean, just somehow by analogy, it should be a group object in a category of smooth categories, whatever that is. And so what I'm going to spend a little bit of time explaining is what we mean by that. And so we're either going to work in a two category of smooth stacks or of Lie groupoids. So for some of you, you probably know these things and it will be review, but you told me I shouldn't assume, so I will say. And then once we know what the two category is, then we can just say we take group objects in it, and that's a smooth two group. Questions so far?
So, yeah, my question since the beginning is what are examples of these? And I think you want to study this example coming from.
Yeah. So the sort of the famous example that motivated this is that people want to study physicsy kind of people want to study something called the string group, which should be like a spin group, but we keep going, and you can prove that there's no finite dimensional model of the string group. So you either have to work with infinite dimensional spaces, or other people have shown that you can view it as a two group. That's the most famous example, and it will come back later a little bit.
So you will show the example.
I mean, I'll say roughly like where
What it is. Okay.
And I'll give other more down to earth examples. Okay, so let me.
It's like for me thinking without examples.
Yeah.
But you said that the line bibundles are example.
Yeah. Okay, so let's think about Yeah, what's a Lie groupoid? So it's a diagram in manifolds. I have two manifolds. X0 is the objects, X1 is the morphisms, and I have maps between them. So if X1 is the morphisms, I should have source and target maps. And if X0 is the object, I should have an identity for every object. And then I should have, so I think about phi in X1 as being a map from its source to its target. For every object, I have the identity. And then I also have composition, which I haven't drawn on my diagram, but if we can compose, if the source of psi and the target of phi are the same, then we should be able to compose them. And so that means we should have some kind of map from this fiber product here. And in order for this fiber product to be a manifold, we require that S and or T is a surjective symmetry. And then we have axioms that say composition does what composition should do, and so on. So that's what a Lie groupoid is. And so the idea is that we've taken morphisms and objects and composition, everything that categories have, but now we are also saying, well, we also want there to be some manifold structure going on, and we want that to be respected. So every manifold is Lie groupoid in a boring way. We don't add any morphisms. Another first example is if we start with a Lie group, and then I can consider the groupoid with one object and morphisms given by that group. And then another example is if I have a cover y over x, then I build something called the check groupoid, which is supposed to be equivalent to x, but my objects now are y, but I want to say that 2 points in y are equivalent if they live over the same point in x. So I put in a morphism for every pair of points that lives over the same point in x, and I compose and all the axioms. Questions about that? Okay, so those are the objects in my two category of Lie groupoids. And let me say what are smooth functors. So you can guess, right? I draw my diagram. Here's my source groupoid X, and here's my target groupoid Y. And I want a map, smooth maps between objects and morphisms that are compatible with morphisms. So if I have a morphism in X from X to X prime, then its image in Y should be a morphism from the images of the objects. I got erased. And it should respect composition. So, and then an exercise for people who are tired of listening to me is to say what's a smooth natural transformation between such functors. So let me give some examples and at the same time, some problems with this definition. So for example, we just saw the check groupoid. And I said that.
Can you repeat what's the check groupoid again?
Yeah.
Sorry.
So objects are Y, points in the cover.
Mm-hmm.
And morphisms are pairs
Mm-hmm.
that live over the same point downstairs.
Oh, okay.
So there's exactly one morphism between any two pairs of points living over the same X.
Okay, cool. And the composition is?
So if Y1 and Y2 live over the same point, and Y2 and Y3 live over the same point, then Y1 and Y3 live over the same point.
All right.
Yeah, so nothing complicated.
Okay, see. Okay, cool.
Great. So we've got that guy, and he's supposed to be equivalent to X. This is a groupoid model for X, where maybe, so we should definitely have a smooth functor from one to the other, and we do. Okay, so here's my Y check. So objects are Y, and I can send a point of Y to a point of X. That's exactly what my covering map did for me. And upstairs, well, I can take either of these two compositions because they're equal. So I have a pair of points which live over the same point downstairs, and I just take that point downstairs. And you can show that it satisfies the conditions that we need, but this is supposed to be an equivalence of Lie. So we ask, when can we go back the other way? And the answer is that we can only go back the other way if this cover had a section. So if it was a pretty stupid cover to begin with. So that makes us a little bit sad about this definition of smooth functors. Something is going wrong with our inverses. Let's look at another example. Okay, I kind of assert by notation that maps from X into point mod G should be the same as principal G bundles of X. So let's look at smooth functors from X into point mod G. So, okay, I have no choice on objects. Everything goes to the point. And then at first you think, oh, I have some choices up here, but no, because everything up here is the identity morphism. And so it has to go to the identity morphism over here, which is 1. And so there's only 1. And so we're not getting principal bundles. On G, we're getting the trivial G bundle. But if you do the exercise with smooth natural transformations, you see that we really are getting the category. So the automorphisms are right, but we're missing a bunch of objects. And so the problem that we run into is that lots of morphisms that we were hoping to see, they exist only locally. So locally, our cover y over x admits a section, and so locally, this functor has an inverse. And locally, every G bundle is trivial. And so the solution is to sheafify our definition of smooth functor. So this is due to Cronk. And she formalizes it by saying, okay, we do a localization on our 2 category by inverting the things that should be invertible. So called essential equivalence. And the result has a nice geometric description, and we call it bibund for bibundles, the 2 category. The objects haven't changed. They're still the groupoids, but now morphisms are bibundles, which are diagrams that look like this. So here's my source. X, Y, and here's my target Y. And in the middle, I put a manifold. P is just a manifold. It's not a groupoid or a category or anything. But it has a map to X0, a map to Y0. It has a left action of this groupoid. In particular, it has a map gamma L from this fiber product to P over Y0. And it has a right action of the target. And the thing that's not symmetric about this is that the right action should be principal. And in particular, alpha should be surjective. And okay, that's all I'll say. Now we'll see some examples in a minute. And then a 2 morphism is an isomorphism of bibundles, meaning maps between these middle manifolds here that are compatible with everything else. And so these are going to be, this is the 2 category that we're going to work in, and we're going to look at group objects in this 2 category. But first, let me give a few examples because bibundles diagram was a bit overwhelming for me at first. So let's go back and revisit our maps from X into point mod G. So here's my source, X over X. Here's my target, G over nothing. I need to put P in the middle. And it should have a left action, okay, but that's just a map from X cross P over X to P. That's a map from P to P. It has to be the identity. So there's no information on the left action side, but on the right action side, we should have a map from P cross G into P, which makes it into a principal bundle. So we are exactly recovering principal bundles. So this is good. We fixed one problem. Another thing I want to say quickly is that, well, if this category, 2 category, is really a localization of the one that we started with smooth functors should give bibundles. So there's a construction that's called the bundleization. And what we do, we put pointy brackets around our functor F, and that means we're taking a fiber product here. It consists of points, objects, X, morphisms in Y, which go from something, the source, whatever, into the image of X under the functor. And so you can see that it has a nice map in both directions. But the key feature that it has here is that actually this alpha has a section. We just take X to X and then the identity map. And that exactly characterizes the bibundles which come from smooth functors. So this is a fact that a bibundle is equivalent to the bundleization of a smooth functor exactly when alpha admits a section. And in general, all we can say about alpha is that it's principal. So locally it admits a section and locally it's a smooth functor.
Emily?
Yeah.
So like before you were talking about Lie groupoids and smooth functors between them. And I guess if we have a Lie groupoid and a smooth functor, we can just regard that as ordinary groupoid, you get a functor, normal kind of functor.
That's right.
Is there a way to go from a bibundle to a ordinary?
Yeah, I mean, you can always choose a section that's set theoretic. And then I can read off my ordinary functor as section and then apply this guy. And it might, yeah. Okay. Okay, and so which bibundles are invertible? They're the ones where not just alpha, but also beta was. So now our diagram is kind of symmetric and we can take the mirror image and we have to put inverses on our left and right actions. Right and left actions.
I have another like philosophical question. At
Yeah.
the beginning of the talk, we talked about two groups. We had a category that was
Two groups.
sorry, two groups, which is a category, and he didn't demand there that it be a groupoid. But now,
That's
when we
right.
got into the smooth setting, we did start looking at
Right.
groupoids. Is there a good reason, or is it just?
So all category, I mean, you can that it's a groupoid, that the morphisms are invertible. I think this comes automatically when you say that the condition on tensor products.
Oh, okay. You mean even for two group abstract two group?
Yeah. Okay, so here's the definition of a smooth two group following Chris Schomer-Priest. A smooth two group is a group object in this category of bibundles. So that means it consists of a Lie groupoid, which we call G, a bibundle which gives multiplication, so we call it M, but that's a manifold that lives in between G0 cross G0 and G0. And then we have two morphisms, for example, the associator, the unitor. And a definition is that in the special case that M is not just a bibundle, but a smooth functor, that's when we say it's a Lie two group. So these guys were invented first, and they're described by Baez and Lauda. And then later, we realized, okay, maybe we want to consider more general kinds of multiplication. So that's why we use the word smooth two group. So let me give an example. And so this is supposed to be like the categorical version of a torus. This is, you can read about this in a paper of Nora Ganter. So here's the input data. Start with a torus T, and it's Lie algebra with the exponential map. Have the kernel, and the check, and I fix a bilinear form with integral values, and then I extend linearly to my Lie algebra T. So that's the data that Nora needs to define a two group. And then I'm going to tell you what is a Lie groupoid. It's boring. So the objects are T, the original group, and then we just stick in a copy of U1. So we don't add any morphisms between non-equal objects, but for every object, we stuck in a U1 worth of automorphisms. Then we want to define a bundle M, a space M, which lives in between. And because this guy is trivial, like it's just the product of T with U1, it should be a principal U1 bundle over T cross T. That's what we're looking for. And here's what we do. We take the trivial bundle, not over group cross group, but we say it's trivial when we pull back to Lie algebra cross Lie algebra. So we have U1 cross Lie algebra cross Lie algebra, and we oppose an equivalence relation, which is very tiny here because it's not that important for us, but it comes from J. And so now we get a non-trivial principal U1 bundle over T cross T, and it fits nicely into here. And that's our multiplication. But on the level of objects, it really is just multiplying two things in here. So it's extending the ordinary group structure that we had on the group, on the torus.
So J is just the first Chern class of this U1 bundle, is that right?
Yes. So this was an example where we started with an ordinary group and we built a thing on top of it, and it fits into a big family, which is what we call categorical central extensions. And so by that, I mean a two group that lives over an ordinary group, and the kernel, in some sense, which I'm not going to define too precisely, is one of the two groups that we talked about with one object. And the morphisms are an abelian group A, which are the automorphisms of one. And so this is an analogy to the more classical story of central extensions of groups, which we know are classified by H2 as abstract groups. And if I want to take central extensions as Lie groups, then I need to consider the group cohomology with topology. So this is SM for Siegel-Mitchison cohomology.
Is every smooth two group with one object that point mod
Yes.
any group?
Yeah. It has to be abelian. It's like an Ekman-Hilton argument. It has to be abelian. Okay, so let's first do the discrete abstract version without any Siegel-Mitchison. So this is, it's due to Sin, who was a student of Grothendieck, who I think is very cool. She was in Vietnam during the Vietnam War, and she did her whole thesis by correspondence, writing letters. So every time we feel bad about Zoom meetings, I think about this. And so you can still find it online, like handwritten, but then it's written in a typed form by Baez and Lada. So if we want to define an extension of G by point mod A, we need to give a 3 cocycle alpha. She shows that if we have cohomologous cocycles, we get equivalent extensions. And any 2 group, abstract, like in the discrete or abstract version, is equivalent to some kind of extension of its isomorphism classes of objects by point mod A. But the caveat here is that this is not necessarily central. And the formulas I'm going to give only work for central.
Is this alpha exactly this associator or
It
something?
will be. Yeah. So let me show you here the construction. That's why I chose conflicting notation. So just like Nora did, we take a kind of boring groupoid, G times A is our morphisms, meaning that morphisms between G and H, there are none if G is not equal to H, but if G is equal to H, we stick in a whole copy of A. Multiplication on both on objects and morphisms just comes from my group structure. But then what is alpha? Well, it's supposed to be a map from GHK to GHK. These guys are equal as elements of the ordinary group, meaning that there's an A worth of automorphisms between them. So we need to choose one of them, and that's exactly what alpha does for us. It picks it out. And the cocycle condition, which has 5 terms, is the same as the pentagon axiom. Okay, the smooth version. So this is a whole family of 2 groups, right? This is all abstract 2 groups. Smooth version is due to Schomer-Priest, and I'm not going to get into too much detail, but he proves that smooth categorical central extensions are classified by H3. And then our favorite example is string, which is the categorical central extension of the spin group classified by a generator of H3 with coefficients in U1. For n at least 5, that's just Z. So we only have 2 choices of generators, plus and minus 1. And they're not isomorphic as extensions, but abstractly as smooth 2 groups, they're isomorphic. So there's just one string group. Questions? So now, finally, we know what a smooth 2 group is, and so we can define a principal 2 group. And if you look in the literature, well, the way that you look in the literature for principal bundles for ordinary groups is that we're just so used to working in them with different ways. So some people work with flat groups, and then they just study holonomy, basically, and then they give a map from pi 1 into G, and they say this is a bundle. Or other people give in terms of check data, things like this. So we eventually decided to just go back to the beginning and say, what's the most basic geometric definition that we could give? And then do we recover all these other things? And we do. So a principal G bundle on a manifold X is a Lie groupoid P that lives over X with an action of G, which is locally isomorphic to the trivial bundle. So I've put a bunch of, now I owe you many definitions. What does it mean for curly G to act curly P? And what is the trivial bundle? What does it mean to be isomorphic to it locally? So an action of G is a bibundle, call it act, which lives between the groupoid P cross G and the groupoid P. And then it has 2 morphisms. Okay, they're not we can't literally phrase them in this way. We should phrase them in terms of commutative diagrams, but they essentially say that if I act by one, then it's the same as doing nothing. Or if I act by G and then act by H, that's the same as multiplying GH and then act. So they're the usual things that we want an action to satisfy, but now they're two morphisms which satisfy some conditions. Okay. What does it mean to be locally trivial? It means that there's a surjective submersion of X and an equivariant invertible bibundle that goes from Y cross G. That's the trivial bundle over G over Y into the pullback. So we can do some pullbacks. And so now I owe you the definition of equivariant. But before I give it, let me just say that once we have that definition of equivariant, I'll be able to say what's a morphism bundles. It's an equivariant bibundle between P and Q. And then we can say what are two morphisms? They're morphisms of equivariant between the bibundles. So finally, what's an equivariant bibundle?
Sorry, Emily, I have a question about the local triviality.
Yeah.
So you could have imagined a different definition where you only, you have a stricter condition that
Yeah.
subjective submersion is the actual cover, an open cover. So do you need this generality, or does the stricter notion?
A lot of things you can do with just with open covers. Okay, so what's an equivariant? On an eraser. Bibundle. So it's phi from P to Q together with a two morphism that makes this diagram commute. So if I start on P times G, I can first act on P and then apply Q, or I can apply phi and end up in Q, or I can apply phi and then act on Q. And so we have a two morphism, which we call epsilon, which is a natural transformation between those two bibundles. And the upshot is that we get a two category, which we call bund curly G of X. And sometimes to remind ourselves that really we're working in bibundles. So this is the definition, and this is the thing we're trying to classify. So ultimately, our goal is to understand this moduli problem of curly G bundles. And the idea to start is to study the simpler subproblem of trivial G bundles. And then the theorem is that, that the original moduli problem is a stackification of this pre-stack. So what is the two category of trivial G bundles over X? It's got one object, the trivial G bundle, and then its automorphisms are a category. An automorphism is given by a pair of rho epsilon of a bibundle and an equivariant structure. And then morphisms are natural transformations between rows that are compatible with the epsilons. Now let's go back to the ordinary G bundle story where we think about automorphisms of the trivial bundle, and we know that those are given by sections, right? If I have a map from X cross G to X cross G, it's always of this form. That's determined by a section sigma. And if I want to compose maps determined by sigmas, it's the same as multiplying the sigmas, right? So the automorphism of the group of trivializations is the same as the group of maps from X into G. And we have an analogous theorem here, which says that we have an equivalence of monoidal categories between the monoidal category of automorphisms under composition, and then the monoidal category of bibundle sections under multiplication. So once we have that, now we can talk about check data. And the results that we have on the archive are for the discrete setting, and we're working to generalize to any categorical extension. So let's recall that for an ordinary principal G bundle, I can classify it by choosing a cover and then a cocycle row. which satisfies the co-cycle condition. So row of y1, y2 times row of y2, y3 is equal to row of y1, y3, which we can say more compactly as d rho is equal to 1. And so here's the idea for how we would do the same thing in our higher categorical setting. So first I'm going to start with a cover over which I can trivialize. So over y, I'm assuming that I have a trivialization and therefore I get transition functions on the overlaps. And so my transition functions are these rho hat epsilon hats that we saw. And then we know that, well, actually I do a further step that says, okay, let's refine U, this cover, so that the section that corresponds to rho is actually a smooth functor, not just a bibundle. I can always do that. And so then here's my rho, it looks like this. And now this condition that we had over here is now data. So now we have an isomorphism between some compositions of rho hats. And in terms of the section rho, these natural identifications, gamma, become an isomorphism in this category of maps from y cross y into G, which is a map from that threefold product into A, which gives this isomorphism here. Okay, so instead of having an equality, now we have an isomorphism, which has a name, and then it should satisfy some further condition. That's the idea. We can summarize it.
So this A is you're in the special case where you're two groups with two group
Yeah,
is of that form.
yeah, that's right. Otherwise, yeah, we're not going to be able to classify. We need a group. We need, yeah. Okay, so the summary is that we need three pieces of data: a cover, a cocycle, and a cochain, satisfying these homology type conditions. And let's compare, if I had that data, how would I actually produce a bundle? So in the classical setting, what do? My bundle is a quotient of y cross G by the relation determined by rho that says that y2G is equivalent to y1, and then not G, I've twisted G by rho. So we want to do the same thing in groupoid land. So I have the same objects that I did over here, y cross G, but instead of just taking an equivalence relation, I add in isomorphisms. So now anytime I have a pair like this that was identified before, now I have a worth of automorphisms between those guys. And I have some composition, which I've written here kind of small. It's not too important, but it uses alpha and it uses gamma. So the gamma and the alpha are starting to appear to define this composition. So we can prove that this is a principal G bundle, which is equivalent to the guy that we started with. So that's a classification in terms of kind of check style data, trivializations and transition functions and things like that. If we now consider flat G bundles, and so just formally, let's say that a flat curly G bundle is we put the discrete topology on curly G, and we look at bundles for that guy. So the classical story is that it's determined by homomorphisms from pi 1 into G, and we can generalize that, at least in some settings. So we want a homomorphism of two groups from pi 1 into curly G. What is that? That's a homomorphism of the underlying groups. But okay, we can think about these guys as monoidal categories, right? So we want our for a functor to be a homomorphism, it should be monoidal. And that's what gamma gives us here. It tells us that rho of AB is isomorphic to rho A rho. This theorem is only true for X with contractible universal cover.
Emily, so this principle of G bundle, is it also a regular G bundle? There
is underlying a regular G bundle. Yeah, so we have a functor from here to here that's forget gamma.
Was that obvious before this classification, or is it?
It was hard to formalize. Like we were like, oh, you take equivalence classes along fibers of your group, you know? So it's much more clear from this description.
And so how do we think about this additional data that we need to make it a principal crypty G bundle? I mean, I guess it's this gamma thing, but is there a way to think about that gamma?
Yeah. So if I fix a row, fix a pair here and look at the fiber, all the gammas in that fiber, they're cochains, but if I look at two different gammas in that fiber, they say gamma and gamma prime, that will be closed because d gamma is equal to d gamma prime is equal to rho star alpha. And so it's a principal bundle for Z3. So the fibers of this map are basically gerbs. Gerbs. Know if that would answer you if you like thinking about gerbs, but
Not so much, but at least it's an answer. Okay.
In the flat case, do you have a definition when X is not a K by one?
we have a definition, we don't have a classification.
You expect it to only involve the two skeleton?
Yeah, right. So we should replace this guy here with the fundamental two group. And my master's student is thinking about that.
But it could be the case that there might be no way to put this gamma, right? You said that the
Yeah.
N2 one, it's like a torso for this set,
Yeah.
but it could be the case that
There is always a, and actually,
there is always a.
well, we definitely prove it for U1. And that's one of our applications. So, and in our application, we only care about surfaces. And so that's why we only bothered proving easy version of our theorem. I think that's the next thing. Yes, okay. So here's an application of all these kind of category theory ideas. Why should we bother? To Chern Simons theory. And specifically, you deal with finite groups. So not just discrete, but actually finite. And so then Chern Simons theory is known as Dijkgraaf Witten theory. And to build it, you need input data of a finite group G and a 3 cocycle alpha. So it's the same ingredients, maybe it's suspicious. And then, I'm not going to tell you the whole story, but Freed and Quinn construct this line bundle, which I'm going to call LFQ, over the moduli space of ordinary G bundles on all Riemann surfaces, which has the property that if I pick my favorite Riemann surface, I restrict to the moduli of bundles on that surface, and I look at the sections of my line bundle, it's the value of Dijkgraaf Witten theory on sigma. So here's a line bundle living over the moduli space of principal bundles. Now we also produced some kind of object living over the moduli space of principal
Can
bundles.
you say quickly what's this the theory? Surface? No. Okay.
I mean, I can say in context of our theorem, but I don't want to get. Yeah.
It comes from some equations.
Yeah, it comes from, they do some like transgression with this alpha and they define. Okay, but here's how we do it. We look at this space of flat G bundles living over the space of ordinary G bundles. The fibers, that thanks to Joel's question, are gerbs. So and so if we take isomorphism classes, we get isomorphism classes of gerbs, which is U1. So we get a U1 bundle, and it is the same U1 bundle as that guy. So that's what we prove. And so we give a different construction that does not use transgression and things like that, but it uses higher category theory. And so this is, in other words, this moduli space here is a categorification of this line bundle. And okay, so far we can't do anything with it, but we hope that maybe we could. So for example, the question is whether the functoriality also works out well. So suppose that we have a 3 manifold with boundary, then Chern Simons theory is supposed to produce a linear map between the two vector spaces here. And there should be a way to describe this in terms of restriction of G bundles. So we start with G bundles on the whole manifold, and we can restrict to either of its boundaries. And so we know that elements of here are sections of this guy. Sections of this guy are isomorphism classes of lifts of bundles.
So this T is like a vector space. What type?
Yes.
Just like sections of something.
Yeah. I mean, because of this description, it's
Yeah.
sections of a line bundle, so it's a vector space. Yeah.
So the finite is important there because then H3 of GZ is isomorphic to H2.
Mhm.
It's one. There's one.
Yeah. And
That's the natural So high level could understand it by S1 bundle.
And also because Chern Simons theory is much harder. So Dijkgraaf Witten theory is kind of a toy case.
Model for that.
Yeah, and I'll explain a little bit now of some work in progress or some ideas. So what happens if G is
Why flat though here? Because before you were telling me that you have the this description involving the gerbs for any for bundle.
right, but we want flat gerbs because that's the thing that gives you one. You want to consider U1 as a H with coefficients in discrete U1. Okay, so here's a little bit, roughly the story for general of G compact and alpha Siegel-Mitchison 3 cocycle. Well, first of all, the data of a Siegel-Mitchison 3 cocycle is more complicated than just a map from G cross G into A. And there's no Freed Quinn line bundle. The best we can do is something called the pre-quantum line bundle, which again lives over the moduli space of flat bundles. And it's just pre-quantum because we don't get states by taking sections. We have to choose a connection. So this line bundle is equipped with a connection whose curvature is equal to the Atiyah-Bott symplectic form. And once we've got that connection, we can take roughly holomorphic sections and recover the quantum states. So the procedure is a bit more complicated. And so far we're over here. We show that, at least in the case of a categorical torus, like Nora Ganter's work, we do get a line bundle still, and it is the correct line bundle. But what we would like is to give a construction of this connection in terms of the geometry of this moduli space. So we want our two category to also categorify the connection, otherwise maybe it's just a coincidence. Yeah. So our goal is to categorify the pre-quantum line bundle with its connection.
Sorry, what's the relation with Ganter's work? Like that's the case when G is a torus?
Yeah.
That's, I mean, that will be the script T in that case?
Yeah. And the relation, she didn't study this, but we took the T from that she describes and we studied our bun flat T. And we found the transition functions. I think assuming, to be honest, assuming all the classification from the previous slide is true. We just started from the holonomy data, so that the holonomy data gives the right thing.
Oh, you mean because for the classification of the previous slide, it was only a theorem in the case of the
yeah. So we started with this data. So I mean, I can start with this data, and that does define for me a two category, and that two category gives me the line bundle, but not yet the connection. And we think that possibly to understand the connection, we'll need to define what are connections for two group bundles. That's all the work in progress. Okay, so the last thing I want to say is a few other applications and future directions. So one is to string geometry. So for example, we know that a spin structure on an oriented manifold is an extension of the structure group of the tangent bundle from SON to spin N. And analogously, a string structure is a further extension to the two group. And so all of the things that physicists like to do with spin structures, you can ask, can we even formulate same sort of things like Dirac operators and things like that?
Again, is this two group you were mentioning?
Yeah. And right. And so to do that, we need to understand at least what does it mean for this thing to extend to a principal bundle. String. So that's why that's a big motivation for understanding principal two group bundles in general, is to apply specifically to the case of principal string bundles. Another thing is a relation to loop spaces. So this is due to Waldorf. He has something which he calls the transgression regression machine, which is fun to say. And he says that instead of studying line bundles on a loop space, we can study gerbs on M. And so gerbs on M is like a two-groupy kind of situation. And this is kind of like a give and take situation where if you want to study line bundles on LM, you have some struggles because you have to deal with infinite dimensional spaces. If you want to study gerbs on M, everything is finite dimensional, that's great, but you have to deal with higher categories. So depending on what theorems you have or what your strengths are, this might be good for you. And so, for example, spin geometry on LM comes from principal bundles on LM, and string geometry on M comes from two group bundles. So there should be a correspondence between those. Projective representations of the loop group should correspond to weak representations of the two group. And to combine these things together, we talk about equivariant elliptic cohomology. So Nora Ganter has shown that the Freed Quinn line bundle is a natural home or twisted equivariant elliptic cohomology. And so this, from Nora's perspective, is that two groups are intimately, like inherently related for elliptic cohomology. We need two groups. But on the other hand, if you look at Kieran Luke's thesis, he builds a construction of equivariant elliptic cohomology using loop groups, no two groups anywhere. And so the expectation is that these two pictures are exactly related by this machine, but that's not understood at all. So now it just looks like two parallel things that say they're doing the same thing with totally different ingredients. So we'd like to understand that too. That is all. Thank you.
No.
Thank you.
Yeah.
Other questions? Remarks?
I remember hearing like a long time ago about something about relation to elliptic cohomology and this thing called the Witten genus, which was supposed to be related to this.
I can't say anything precise, but yeah, these are words that people say.
One of the Stoltz-Teichner project.
Uh-huh.
So what would be the, for principal G bundles, maybe the old category, we have a classified space for them, right?
Uh-huh.
And go back into the bundle. So what would be the
Yeah. So we can only say this in the discrete case properly for now, but we should be able to take like white mod curly G. And this is a two category with one object. But we don't, I don't, at least maybe my collaborator does, but I'm not totally comfortable with how to make this, how to formalize the manifoldness in a two category.
would you have like a bar or two, a bar construction or two
I don't know, maybe, yeah, maybe that's a good way to think of it.
groupoids, right? They have a classified space of groupoids. So,
Uh-huh.
you know, for loop groups, there are people who work on the K theory of loop groups or something. Moody groups in general,
Uh-huh.
very interesting stuff.
Yeah, I mean, yeah, my co-author tries to understand Freed Hopkins Telemann.
Drew has some stuff on that.
It'll all be related.
And the twisted phenomena also.
Right, yeah, so. Right, we should be able to define twists for elliptic cohomology. But for this, we need to understand graded principal two-group bundles. It's another thing on our to-do list.